So to continue our discussion on pH and pOH of strong acids and bases, we've been taking plenty of different strong acid-base solutions and comparing them and identifying their pHs from their concentrations, but let's make sure we can go both ways. Namely, in this case, what is the hydroxide concentration in a solution having a pH of 3.55? Well, first of all, since I'm asking about a base, something with hydroxide, I'm not going to think pH, I'm going to think pOH, because the hydroxide concentration is what I'm interested in, not the proton concentration. And if the pH is 3.55, the pOH would have to be 10.45. Then, of course, if I want to go from this negative log of a number back to the number from which it comes, let's not forget that pOH is found by simply taking the negative log of the very thing I'm seeking, hydroxide concentration. And when I did that, I get this. So if I want to think backwards, I would think this way. I'm really taking negative 10.45 and finding what used to be called the anti-log of this number to identify the hydroxide concentration. And the anti-log is also referred to as 10 to the x. X is the anti-log of a base 10 number. And so on a TI calculator, that can usually easily be found by pressing second function and typically speaking on a TI, the log button, because if you look at your calculator and directly above the LOG button you see this 10 to the 6, then it is the second function of that key. So in this case, I press second function log, enter negative 10.45, not 10.45, press enter, and I get the value 3.55 times 10 to the negative 11th. And don't forget, that's the molarity, moles per liter of hydroxide ions. Now, something else we should consider as well. Let's not forget that logarithmic values here, base 10 log values, differ by a power of 10. For every one logarithm point, you have a tenfold difference in the values you're measuring. And that's very important when we're asking a simple problem such as this. We have solution A, and solution A has a pH of 2.39. And solution B has a pOH of 9.61. And I'm asked to compare which is more acidic and how many times more acidic is it. Well, it's easy to answer the first question. All I should do is compare pHs. The lower pH would represent the more acidic solution. And so I can't really compare apples and oranges. So instead, I convert this pOH to a pH, and it becomes 4.39. Now I can answer the first question. Obviously, if solution A has a pH lower than that of solution B, it's more acidic. And it's easy even without a calculator, because of the numbers I have here, to answer the second question. I notice the two pHs differ by exactly 2 points. In other words, they differ by 2 powers of 10, or 100. So in fact, solution A is 100 times more acidic than solution B. If you jumped into solution A and swam around, you'd be bumping into protons much more often than if you jumped into this guy. You'd be glancing all the way across the solution. Oh, there's a proton. But here, you're bouncing off them like a pinball. So, let's make sure we can work both ways with these problems. Here I'm asked how much sodium hydroxide must be added to 3 liters of solution to create a pH of 3.150. Now, the first thing I do is remember when I'm given lemons, make lemonade. And we're talking about a strong base here, so pHs don't help me. I'm much more interested in pOHs. And the pOH of the solution would have to be 0.850 if the pH is 13.150. Now, something I try to impress upon all my students. Don't think of a pH or a pOH as some fancy number. Literally, when you're given either one, a pH or a pOH, you have been handed a molar concentration, moles per liter, of either protons or hydroxide ions. So if I'm going to know how many moles I need to add to this many liters of sodium hydroxide, it would be nice to know the molarity of the hydroxide ions. And that's easy because I will take second function log on my calculator of negative 0.850. And when I press I get the value 0.141. And I remind myself that that is moles of hydroxide per liter of solution. Now, this problem wants to know about the amount of sodium hydroxide. And because sodium hydroxide dissociates in a 1-to-1 ratio, 1 mole of hydroxide is the equivalent of 1 mole of sodium hydroxide. Meaning, this is how many moles of sodium hydroxide I need. Of course, I have to account for the volume and cancel it. And if we want to make 3 liters of this solution, this represents the number of moles of sodium hydroxide I'm going to need. And it comes out to 0.424 moles of sodium hydroxide. And that's a sufficient answer because it asks how much. It didn't say what mass. But of course, if I wanted the mass of sodium hydroxide, I'd just convert moles to mass using the molar mass of sodium hydroxide. So no sweat. The emphasis, once again, is once you're given a pH or a pOH, you're really given a molar concentration of something. Very important to keep in mind. Here's an additional problem. What mass of hydrochloric acid is in 2 liters of solution having a pH of 1.88? Now, in this case, I have been given an acid, so pH is what I'm interested in. But of course, I remember that if I have a pH, I really have a molar concentration of protons. So if I take second function log of negative 1.88, my calculator gives me 0.0132 molar protons. So, how much acid did we need? Well, I'll give myself some space down here. We want this many moles of proton per liter of solution. And of course, we're trying to create 2 liters of solution. So this is how many moles of protons I want, but I'm specifically asked for a mass of HCl. Well, once again, since hydrochloric acid is a strong acid and completely dissociates, and because it's monoprotic, 1 mole of the acid is equivalent to 1 mole of protons. So if I want a mass, all I need to know is the molar mass of HCl, and 1 mole HCl has a mass of 36.5 grams HCl. Everything cancels except the mass of HCl in a solution to give me that particular pH. And it comes out to 0.962 grams of hydrochloric acid to create the solution I wish. As one last example, let's consider this problem right here. How would you prepare 250 milliliters of aqueous solution having a pH of 12.88, so I've been given a molar concentration of something, using sodium hydroxide? Of course, this is a high pH, and that's what we get putting a strong base into water. But once again, if I've got lemons, I'm not going to try to make orange juice. I'm going to make a lemonade. Therefore, I'm going to think in terms of pOH for this base. And the pOH of the solution I want to make is 1.12, which means that we want to know what the second function log of negative 1.12 is, so that we can get our hydroxide concentration and do the problem. And it comes out to 0.0759 moles hydroxide per liter solution. So, to give myself some space down here, and I will rewrite, sorry about that, that we have, or we want, 0.0759 moles of hydroxide in every liter of our solution. And of course we're trying to create 0.250 liters of solution, 250 milliliters. And because sodium hydroxide dissociates completely in water, you get 1 mole of hydroxide for every 1 mole of NaOH. And if I'm going to describe how to prepare it, I'd like a mass. And 1 mole of sodium hydroxide has a molar mass of 40 grams. Meaning I'm going to require 0.759 grams of sodium hydroxide. But that doesn't answer the question how to prepare the solution. But the answer would be the same as all of those in the preceding videos on solution preparation. Namely, I would take 0.759 grams of sodium hydroxide, place it into a 250 milliliter volumetric flask, add enough water to completely dissociate the sodium hydroxide, and then add sufficient water to create exactly 250 milliliters of solution. That's how we should prepare it.